Alright, we're going to start off with why we need telescopes and then talk about the types of telescopes and where we put them. So, we need telescopes for two reasons. We want large collecting areas. So that's what this little animation is. All of these lines, imagine that as starlight coming down from space. And if you have a small opening, you're not going to catch very much light. So we will build the biggest telescope that makes sense, that we can afford, so we catch more and more light, and we catch more and more light, and then we direct it, kind of compress it down, and when you do that, you get to see fainter objects. So we want more collecting area to catch more light to see fainter objects. We also want a large telescope because when you do that, you also get better resolution. And we call it angular resolution. So let's click over. Angular resolution is going to mean how small of a detail can you resolve? What is the angle, the angular separation of the smallest thing that you can see? And so if you were to look at a pair of binary stars with a good large telescope, you would be able to resolve that there are two stars. 1, 2. You would see the detail. If you were looking at the exact same thing but with a smaller telescope which didn't catch as much light, you would also not get as much detail. It would look like one larger, blurrier object. So you want more angular resolution, better angular resolution in order to tell what's going on. When you buy a phone or a TV, you're looking at pixel count. You want more pixels because that means a better resolution. But when we talk about resolution, we're talking about how small of a detail can you discern. So we actually want to be able to discern small details. So we actually want a smaller angular resolution. That would mean better. With my telescope that I own, I control the magnification by switching out eyepieces. And I could magnify Jupiter when I look at it with up to 200 times magnification, but it doesn't look good. It looks blurry, the image jumps around a lot. So I have a limit to how much I can magnify it that's set on my angular resolution. So if I'm walking by Target and I see the cheap little telescopes for sale and it says, you can magnify 200 times, well, that tiny little telescope's going to give you a bad image. You can magnify it 200 times, but it's not going to look nice. Don't buy a telescope for the magnification. There are two main types of telescopes. The historical type is called a refracting telescope, and we'll go through that one first. The refracting telescope uses glass lenses to refract light. Refract means to bend, so just think of your glasses. And you have two lenses in a refracting telescope, so here's a cartoon of it. Your larger objective lens is going to gather the light up. The light will bend and eventually approach a focus point. We call it a focal point. But then you need an eyepiece or a second lens to make the light rays parallel again. And that is just so that way if you look through the telescope, it would look in focus to you rather than it being blurry. Notice how the light rays here on the left are more spread out. The point of the telescope is to gather that light and condense it down tighter so that it could fit into your eye or fit into the camera opening. The way the light rays would go through here, so let's follow one from the top of the flowers, top down through the bottom of this lens and then over to your eye or to your camera. A refracting telescope flips the image. It flips it top to bottom as well as left to right, and that can be really disorienting when you're looking through a telescope and you're trying to pan it around the sky and adjust it, because what you're looking at is flipped. Right. Here is a refracting telescope. Its opening is 40 inches across. This is no longer used to do science. This is no longer competitive. For scale, here, check out the person down here. The little eyepiece that controls magnification would be back here. The large, heavy glass lens is up here. And all the rest of this tube is to support those lenses. And then you have all of this steel here to support the tube and the lenses. It's really heavy. I think it weighs 6 tons. That's a lot of metal just to hold up 2 pieces of glass. So these are no longer used, except for toys. What we use now for science is called a reflecting telescope. Here is a cartoon of one. Right. There are different ways you can design these, but this is the most basic way. Right. You would have the starlight coming in through the front opening. So the starlight comes in through the front opening, and the starlight doesn't do anything until it gets all the way to the back. And once it hits the back of the telescope, that's where the big round mirror is. So this is going to be a primary mirror back here, the big mirror. And it's curved, so that way when it reflects the light, it condenses it to hit the secondary mirror, just a little tiny mirror up here. And that would bounce it back down through a hole in your primary mirror. Now I have a little one of these. My opening angle of my telescope is 8 inches across, my opening diameter. So if you come observing with me later, you'll be able to see it. Right? Nowadays, if you're doing science, you would just put a camera back here. You wouldn't even put an eyepiece. Most modern telescopes don't even have eyepieces. My telescope has a set of eyepieces that I can change out, so I can change my magnification, but I also have an attachment for my camera. Here's a picture looking down at the primary mirror of Keck in Hawaii. Here's the person for scale, sitting in the middle opening. That's where the light would go through to go down to the instruments. And the mirror is about this big. Right? And this mirror is actually made up, I think, of 36 hexagons. So now we don't even have to make one huge piece, one huge glass piece for a lens. We can make a mirror, which is lighter and cheaper, and we can make it in segments and assemble it on site. So it's much cheaper to do it this way. It's much easier to transport them up the mountain. Right, here's a picture of Gemini. This time we're looking at it from the side. So here's the large mirror at the bottom. Here's a person for scale. There's his helmet. Right. There's that drilled hole right in the middle of the mirror so the light can go through to the cameras or the instruments underneath. The secondary mirror is up here. Before, with the older types of telescopes with the refractors, the bigger piece of the telescope was that big front heavy lens, and that had to be supported up really high, and you needed a lot of steel to hold that heavy lens up high. But now with the mirrors, the heavy big part of the telescope is actually on the bottom, and you can support it from behind, and all you need to hold up at the top is this smaller mirror. So this is a much, much better design. It's much more stable, cheaper, lighter. It just oodles better. See these metal rods holding up that secondary mirror? In this case, there's 4 of them. When the light is going into the telescope, these four rods get in the way. But because it's not in focus to your camera, you're not going to actually be able to see the four lines. What happens is it actually makes those spikes on stars. You know, like when you look at stars, they have little spikes on the side of them. That's because of the telescope. Right. A video showing the inner workings of a scientific telescope. It's all controlled by computer. The people on site keep it working, keep it clean, keep it updated, but the actual astronomers never have to go. You don't want to actually touch any of the mechanisms if you can help it. So a lot of it is robotic, getting the stuff from storage back to the telescope. Drilling holes in a piece of metal is going to allow light from very specific stars through, and then you can take spectra of many stars at once. That gas that you just saw coming out of that hole, that was liquid nitrogen, a coolant that you use to keep your equipment cool, and then it works better. Take out one scientific instrument off of the telescope to put in a new one. Cleaning the secondary mirror. Cleaning the primary mirror. Can you see the hexagon lines on that mirror? And once it's nighttime, then it's ready to go. Operating these telescopes costs a lot of money, and once you have a grant, you have money to pay for it, you pay pretty much by the hour. First you have to apply for it, and if you get it, you pay by the hour. So everything is set up and organized, ready to go before it's your turn. What are you going to look at? How long? What filters? Right. We'll talk about those laser beams here in a little bit. The telescopes move to track the sky. They're basically undoing the rotation of the Earth. Long exposures lets you see star trails. These are star trails due to the rotation of the Earth. So you've got your telescope and you put a filter on it to observe it and take photos, and you use a digital camera and you save it. So let's say you took a picture of a nebula just in red, and so only the red light of the nebula would be allowed through the filter, and you take a picture of it. Chances are it would just be saved actually as black and white. Then you take off the red filter and you put on a green filter, and you just take a picture of the green light that comes through the filter, and you save that as a black and white image, and you do the same as the blue. The reason why we usually will take a picture in the red, the green, and the blue is that is how the human eye works. The human eye is sensitive to red and green and blue. And if all three of them are present, you'd see white. If only two of them are present, you'd see different colors. The combination of these three that allow us to see colors. So what you do as a professional astronomer is you download the image from the telescope, and basically Photoshop, you tell it to, I took it in a red with a red filter, let's make it be red. You make it red. And you get to select the color of red, you get to change the contrast, you get to play with it. And then you say, let's add the green image, and in Photoshop you get to pick the color of green and how much contrast it'll have. And then you overlap a third image on it, the blue, and you get to pick the blue and the contrast. And so you end up with this very lovely picture of a nebula that mimics what your eye would see, but it's misleading. I'm like, it's not what the human eye would see. It was taken as 3 different photos. The color was added back in, and then it was processed and enhanced. So I tend to think all astronomy pictures are photoshopped in some way, shape, or form. They just are. When you do the red, the green, and the blue, you are trying to mimic what the human eye would see, so it's realistic. But if I were to take you guys out and show you this exact nebula through the telescope, you would just see a gray fuzz. You would see no color to it. It's so low light, it's so dim that you can't see color. In low light situations, the human eye, the human brain, it just switches to black and white just to tell what's there. When there's plenty of light, then you can see the color.